Okay, this is Introduction to Structures, Lesson 8, Reactions, Bending Moments, and Shear Forces Functions. So, if you are following the series of videos I'm sharing with you in YouTube, you have been through several exercises to resolve cantilever beams and simple supported beams in terms of reaction, bending moment diagrams, and shear forces diagram, and in some cases, axial forces diagrams as well. So in this particular video, I want to share with you concepts around the function that describe the distribution of bending moments and shear forces. So as I mentioned in the previous videos, these bending moment diagrams and the shear force diagrams are in reality functions in a two-dimensional space that describe the variation cross-section by cross-section of the bending moments and shear forces and axial forces in a beam or in general in any structure in civil engineering. So in the first place, I will present this cantilever beam, but in a general way. It is to say there is no any values, actual numerical values for this structure. We have just a cantilever beam with a fixed support to the left. This cantilever beam have a length or a span of L. This Z represents the position of a generic cross section at any point of this cantilever beam. We have applied a punctual load P at the end, at the right end extreme of this cantilever beam. So these are the conventions in terms of displacement. So displacements are positive in the horizontal direction if they are going to the right, in the vertical direction if they are going up, and moments are positive when they are clockwise, forces are positive when they go up, and forces are positive when they go to the right. So this force P on the structure is negative, evidently. So we are going to define a point A as a reference in our cantilever beam, as you see in the screen. So we are going to replace the fixed support by the effect of this fixed support on this structure, that are basically the horizontal reaction AZ, the vertical reaction AY, and the reactive moment MR, and this is the free body diagram of our structure. We are going to use the equations of equilibrium to establish the values of the reactions, the three reactions we have for this structure. And we can do that because this is an isostatic structure. So we only need the equation of equilibrium to resolve the reactions for this cantilever beam. The equations of equilibrium will be the summation of forces in the horizontal direction, that will be Z, the summation of forces in the vertical direction equal to 0 as well, and the summation of moments at any point of the structure equal to 0 as a third equation of equilibrium. So if we start with the summation of forces in the horizontal direction, with the Z direction, we realize that the only force we have is AZ, so this force has necessarily to be equal to 0 to keep the equilibrium. So AZ is equal to 0, and then we can delete it from our free body diagram because it's not necessary to complicate the scheme. So the free body diagram now have only a vertical reaction and a reactive moment MR. Doing the summation of moments around the point A, we realize that we have this force P multiplied by L, the perpendicular distance, producing a positive moment because the rotation around A is clockwise, and minus the moment MR, which is the reactive moment, and all of this has to be equal to 0 by equilibrium. Then from this equation we can establish that the reactive moment at the point A where the fixed support is installed is equal to P times L. Finally, doing the summation of forces in the vertical direction, which is the Y direction, we have minus P, the negative force applied to the structure, plus AY, the positive reaction we expect to have at the point A, and equal to 0. So resolving this simple equation, we realize, or we determine, that the reaction AY is equal to P. So the reaction is P, and the reactive moment is P times L. After that is we do the sketching of the bending moment diagram and the shear force diagram as we are accustomed to do from other exercises we did before. You see that our z-axis starts at A and is positive going to the right. And we repeat this reference line, this horizontal line we know is the neutral axis for every diagram. We know that for a cantilever being subjected to a punctual load, the distribution between forces will be linear for the bending moment diagrams, and this is the shape of the bending moment diagram, and it's negative because it's on top of the reference lines and because it's producing a hogging deflection. And the shear force diagram, as a consequence, will be constant because the shear force diagram is the derivative of this function that represents the bending moment. And evidently, if you check in the screen, this line in blue is a straight line with certain inclination, certain slope, and this is basically a linear function. And the green line here is a constant function that has as a value a constant value we are going to see in the next. So if we write the equation for this cross section in here, this cross section in the middle of the cantilever beam, and we write the moment at this cross section Z in general. Z is the distance from A to the cross section we are analyzing. We have to the left side of the structure AY, the reaction multiplied by Z, the variable, minus MR, which is the moment, the reactive moment in the cantilever beam. But AY is equal to P, so we replace AY by P. We keep Z, and minus MR is equal to PL based on our previous calculations. So in here, what you see is basically the equation of a line in this two-dimensional space where the horizontal axis of reference Z is located, as you can see in the screen. The only thing we need to take care of when we are doing the bending moment diagram is that the axes we usually use to sketch the moments are positive going down, opposite to the usual convention. As you see, the diagram is negative because it's on top of the neutral axis, and the positive side will be under the neutral axis, of course. And for this reason, the whole diagram for this cantilever beam is negative because the function is on top of this reference lines in this interval from A to L. If we write the equation of shear forces at this cross section, we have selected as a general cross section, and we do the calculation to the left side of the structure. The only shear force that appears is AY, which is equal to P. So the constant function that represents the distribution of shear forces in this cantilever beam is basically a constant function that is equal to P. P is the value of the force, the external force, so the shear force along the whole beam is equal to the external action applied to the structure. So as you see, in this simple exercise, the bending moment diagram and the shear force are actually functions in a two-dimensional space. And of course, as we mentioned before, there is a relation between the shear forces and bending moment. The shear force function is the derivative of the bending moment diagram. Thank you very much.